Good afternoon. Can you all hear me?
Yes.
Thank you. Okay, folks, it's 12:30. We'll get started. So what I said I was going to do today was I was going to first of all start with the roadmap problem. I just wanted to show you an example of what I'm talking about. It's problem 7 on the test. And any problem you get will take this same, at least general form in the beginning. There'll be a situation where you'll start off with an alcohol and you'll be asked to show the 3 alkenes that you could possibly get from that alcohol, A, B, and C. Now, you're not going to know which is A, B, and C to begin with. But what you are going to do is you're going to use ozonolysis in order to determine A, B, and C. Once you've got A, B, and C, then you can do the other reactions. And these are reactions we've already looked at. So let's look at how one might proceed with this. But we need, first of all, to know a little bit of a background about ozonolysis and what it does. Now, I'm not really interested in focusing on the mechanism with this one. It's really more about the pattern. And what the ozonolysis, what the ozonolysis reaction will do is it will take the double bond, and you can see it here, the splits the double bond, and you get a double bond O at each end of where the CC double bond was. So it's not a particularly difficult pattern to understand, but that's what you're doing. You're splitting the double bond and you get double bond O and double bond O. That's really it. Nothing more to it than that. Here are some examples. So if you've got this straight chain one, you'll get double bond O here and double bond O here. Likewise with this one. And you'll see that, remembering that when you've got a CC double bond and it's kind of on the end like this, that's a CH2 where I've got the cursor. So that means that when you split it, you'll get a CH2 to a double bond O, and this one will go to a double bond O. Does anybody have any questions so far? Now, if you've got a double bond that's inside a ring, the situation changes a little bit. We still have the same pattern, but you'll notice that if the double bond is inside a ring, we only end up with 1 product and not 2. But the pattern is exactly the same. All we're doing is, again, splitting the double bond. We put a double bond O on each C, where the CC double bond was. And here, you've got a ring here, double bond is outside the ring. And again, we get 2 products. Does anybody have any questions? Is anybody confused by a pattern that we're dealing with here? Any questions at all? All right.
I do feel like in the ring, the second down,
Yes.
where the double bond split, yes, that there would have been a C, and then you would have done a double bond to the O. I guess I didn't follow that.
Well, but you can see here, I mean, let me draw this out a little bit more, Rebecca. It's not the Rona, I don't think. All right, what are we doing? Do you see that, Rebecca? How if you drew it out with all the C's, that's what it would look like?
Yes.
So if you just apply the pattern, then you can see how we might end up with the double bond O's where we end up with them. Is that okay?
So the one splits off, and the other one then has a double O attached to it.
Well, they both do. You split the double bond, the CC double bond, and both ends of the double bond get a double bond O.
Okay, I see. Thank you.
Yeah. Don't overthink it. I mean, it really is as literal as that.
Okay. That CH2 that's in the loose, like in the diagram by itself, is the one on the end.
Yeah, that's right.
Okay. All right. Thank you.
Any other questions? Okay, so that's really all I want you to see from that, just to get a handle on the pattern. All right, let's go take a look back at the problem here, and we'll see exactly what we need to do to solve a problem like that. So as I had said here, there's going to be 3 alkenes that are going to be formed as a result of this first reaction. It's a simple dehydration process. And the idea would be that you would take off the OH and you can draw a double bond out to anything that has a hydrogen on it. And that means that there'll be 3 possible alkenes that one could draw. So we can draw this one. We can draw this one. And we can draw this one. Let's move this over a little bit. There we go. All right, does anybody have any questions about how I'm getting that? Now, at this point, we don't know which is A, B, or C. So what we can do is, you can see that ozonolysis is part of this, right? Now, the zinc, don't worry about that. That's just a cleanup. That's a cleanup reagent. It's just used to clean up excess ozone. So don't be too concerned about that. Just follow the pattern. So what I would do here is I would treat each of these with ozone, see what we come up with. So for this one, again, you look at the pattern, just split it down the middle, and let's see what we end up with. Is anybody concerned so far? Anybody have any questions? Okay.
Could you show on a second one how you split it up in half, please? And in a third
Sure.
one?
Now remember, Victoria, there's a CH2. Can you see my cursor on this or not?
Yes. Yes.
Okay. There's a CH2 where my cursor is.
Okay.
So when it splits, you see, notice that double bond's outside the ring too. So you're expecting 2 products. Anything where the double bond's inside the ring, you're expecting a single product.
Okay.
Is anybody uncertain about what we're doing here? Any questions?
Sorry, I came into the meeting late because I had Wi-Fi connection issues. Are we going over the test that we just took, or is this like a new section?
It's a new section, Sierra.
Okay, it just looks similar to what we were doing previously.
Oh, it all does. It all does. I had just been through, showing a pattern here of ozonolysis.
Okay, so we're building on what we left off last test.
Mm.
Okay.
All right, and the pattern, just to be real quick here, split it down double bond. This is for ozone. Split it down double bond, put a C double bond O on each end of where the C double bond C is. Okay,
Gotcha, thanks.
that's where we're at. Okay. All right. And now I know this is kind of, I'm just going to say it anyway. Can anybody tell me what we do next? I mean, you know, so we figured out these ozone things. Does anybody have any idea of what we would do next, or is it just going to be completely, or you just have no idea where I'm at with this? I just want to see.
I would redraw them to look a little bit more like the D structures, like open them up and then see where I'm at.
Okay, I mean, that's a possibility, but you know, really, can I paraphrase what you just said, Rebecca?
Yes.
I think what I would be inclined to do is look at these structures here, see if I can reconcile any of these, which are ozone products, by the way, right? Your ozone products, with any of the ones that I drew as ozone products of these guys over here. So this one that I'm circling now with my cursor, we know that this is the product of what we're calling B. So looking at these three structures that I've got here, which I'm going to number 1, 2, and 3, which one of those does it most look like? This one here. Does it look more like structure 1, structure 2, or structure 3?
3.
3. How do you know that, Rebecca?
It's actually Julie who said it.
I'm sorry, who was it? Sierra, sorry.
Julie. No, Julie.
Julie, I'm sorry, Julie. I apologize. So how did you find that out, Julie?
Well, I looked to where there was a methyl next to the double O, the double bond O, which is on, which was, well, actually they both are. But I just kind of twisted the other one around. I don't know, it just looks like it.
Okay, so well, one thing you can do here, you can go look at the pattern here. You've got a methyl attached to a double bond O and a methyl attached to a double bond O. There we go, here and here. And then in the middle, we've got an ethyl and an ethyl, and there's your ethyl and there's your ethyl. So from that, then you could say, okay, well this must be B. All right, I'm going to stop right there. Is anybody confused by the logic that I'm using to identify the magical compound B? Anybody? Any questions? So you're all completely hunky-dory with B, huh? How I'm getting B?
For the record, I would still redraw them because it's harder for me to see the pattern when they look so different.
Well, whatever floats your boat,
Okay,
Rebecca.
thank you.
You want to redraw them, lay them out, make them real pretty. That's okay. All right. Any other questions? B. Everybody, is anybody concerned about B? B. All right. So now I look at the other product. This is the one that I'm circling here. So it can't be B now because B is already accounted for. So we know that we need to figure out which one's C. Is it? So is this product here that I'm circling? Is it product 1 or 2?
1.
Yeah, I hope everybody can see that. I mean, if you stretch it out, just like a rope, that means that this guy must be C.
Also the only one left that has 2 double bondos.
Yeah, because we know that A would lead to 2 products, and we don't see 2 products here, do we, in any of these? So this must be A by process of elimination. Is everybody okay with that? Does anybody have any questions? I don't think it's that bad. I think question 7 on the test is kind of a gimme. I'm going to come out and say it. I'm going to say it's easy points. Yeah. That's all I'm going to say. I'll throw it out there. I say it's easy points. All right, any questions? Any questions at all?
Are we done with number 7? Like this is the
No, not quite. We're getting there, Victoria.
Okay.
Not quite. Because we've still got a couple of things here. We've got B. We know what B is. Now, B is this creature. And we know that when B is treated with H2 and PD, it's going to come up with this compound, which is our compound E. Now, this is a reaction we've already done, but what it does is it takes away the double bond and puts hydrogen and cis on the double bond. So you'd have to show stereochemistry, but this would be B, and that would be E. And D, there we go, A to D. Let's have a look at A. All right, and the reagents we've got there, B2H6 and NaOH, H2O2. That will put an OH on the less substituted of the 2 carbons of a double bond. And he'll look like this. All right, so again, you'll have to know the reactions in order to be able to get that right. But that would be A to D. Any questions? Now we're done with it, Victoria.
Okay.
Does anybody have any questions about number 7? All right, it's not that hard, it's not that bad. Hang on, let me get it out of here. Here we go. All right, let's take a squiz at some resources I have for this. Test 4 files, here we go. All right, so there's a folder here. If I can find it. Here we go. Test, but not a folder, it's a file. Test 4 roadmap examples. So it's got problems and answers very similar to the ones you'll see on the test. There you go. Anyway, all sorts of fun for you. Does anybody have any questions? Anything at all? Because I didn't really want to spend too much more time on it than that. I just wanted to focus on what the ozonolysis does and how that hooks into the problem 7 method, or how you would use it to solve problem 7. Any questions? Okay. So what I wanted to do now was do the infrared spectroscopy, and after that, if I have time today, I'll start on the NMR, but on Wednesday, that's definitely what I'll be doing, will be NMR. And it so happens that that's what the lab's about too. So attending the class will really help with the lab as well. I'm going to send out an email that basically states that. And if people don't want to turn up to the lab, they're going to be having great deal of difficulty doing this on their own, I think. So I think the more information you have, the better.
Will you include which videos to watch for the lab too? for the lab as well?
Yeah, they're actually in the lab. They're in the lab folder. There's a folder
they are.
for it. Yeah,
Okay,
you can take a look. You'll see
okay.
it there. It says IR and NMR resources or something like that. It'll be pretty obvious which ones are for IR and which ones are for NMR. Because they're marked as such. All right, infrared spectroscopy. So what do we use IR for? Well, it's to define functionality. It doesn't really tell us what the structures are. You know, it doesn't solve for structures. NMR can do that. IR can't. What it can do, though, is tell you what kind of functional groups are present. Now, I kind of split these into two parts. A diagnostic, which means that it's able to suggest the presence or absence of a particular functional group. And the other thing we can see is confirmatory, where you can use something, a peak, to confirm what you already know about something, or what kind of functional group it might be. For example, to be able to distinguish between a C double bond O if it's an aldehyde or a C double bond O if it's a ketone. That's what I mean by confirmatory. So we're going to focus first of all on the diagnostic peaks. Now, the diagnostic peaks will allow you to determine whether or not a functional group is present or absent. That's going to be the focus. So let's look at what an infrared spectrum looks like. Let's see if we can get a full one here. Actually, I probably don't have a full one now I think about it. All right. Let me pull up. Oh, hang on. I do have it here. Hang on. Find it. Probably is. Here we go. Right. These are infrared spectra. They look pretty scary, don't they? So an infrared spectrum, you can see it's got a whole bunch of peaks, right? These peaks represent absorptions, and these represent frequencies of infrared radiation. And certain functional groups will absorb at certain frequencies. So what we're looking at here is, for example, I'll give you a good example here. If you're looking at an OH bond, when it's hit with certain frequencies of infrared radiation, what it will do is this. We call that a stretch. And it turns out that OHs will tend to absorb infrared radiation at around this region, which is about 3,000 to 3,500 on the infrared spectrum. So we know that if we've got this wide kind of peak, now there's two kinds of characteristics of peaks that we look at. This is broad. This is sharp. So even this general shape of peak is important. And then we've got strong, which means it comes down a long way. And then we've got this one here, which that would be weak. So we look at how broad or how wide the peak is, and we also look at how far it comes down. Okay. So now we've got a little bit of context. Let's go back to, none on that. All right, let's go back to the kinds of peaks that we're going to see. This is a correlation chart here. This gives you an idea of where you can expect to find certain peaks. This isn't the best of pictures here, by the way, but it's clearer in your actual PowerPoint if you want to take a look at it. It's also in your problems test 4 file.
Will we have that for the test, or do we have to?
Yes, yes. You actually get this whole thing here. See all these pages here? These 2 pages here, Julie?
Yep.
You actually get these pages. It's a bit clearer here. You can see that's the correlation chart. Also, look what I've got down here. I've actually got pictures of what the peaks look like. See? Even that. I've even got that. Right, so you'll have that in front of you.
So we don't really have to remember any of it. We just have to know how to use the charts.
It's a miracle, isn't it, Julie?
Yes, it is.
That's what that's my heart's desire right there. You just said my heart's desire. You did.
It's good.
Yeah, it's beautiful. That's what it is. All right. So there's your correlation chart. And in a 3300 to 3500 region, that's where you can expect to find OH, NH, and NH2 stretches. And they're distinguishable because they have different shapes. So OH, there's actually 2 flavors of OH that we can see. But one thing they have in common, well, there are 2 things they have in common. They're both broad and they're both strong. It's just that in one of the cases, the case B, it's so broad that it actually comes over 3000. And that's going to be your carboxylic acid OH right there. Whereas A, so A is more like this, and B is more like this. Now they're both OH stretches, but they're a little bit different because of the kinds of functional groups they're in. Does anybody have any questions about the OH? In the case of NH2 and NH, you'll see that the NH2 looks like vampire teeth. It's in the same region. The OH never looks like that. And the NH, you'll see, is a bit weaker than the OH, but in the same region. So it's really easy to distinguish between NH and OH. Does anybody have any questions? Now in the 2900 to 3100 region, this is where you're going to find the CH stretch. Now I talk about alkane and alkene there. Now the CH stretch attached to a CC single bond will appear between 2900 and 3000, whereas a CH attached to a CC double bond, because it's shorter, will vibrate at a higher frequency, 3000 to 3100. It's shorter because it's sp2 hybridized. So it's sp3, which is long, and then sp2 is a bit shorter and fatter. So it vibrates at a higher frequency. So I want you to think about this. Let's say you've got 2 things attached to a spring and they're far apart. You can imagine how the vibration might go like this. But if you have them close together attached to a spring, it goes like this. Which one's going at the higher frequency? The shorter one is. Right? As opposed to this. Right? So it's really that simple. I mean, that's what we're dealing with, is those kind of frequency vibrations. Now, it's pretty atypical to have a compound that just has alkene. So really, we can have plenty of compounds that just have alkane, yeah, and those have a pretty predictable peak pattern, and you can see it here. This is for straight alkane. Everything's below 3K, 3000. Whereas the other possibility is going to be alkane mixed with alkene, and that's going to straddle 3000. So you'll have it on both sides of 3000. And that's, again, you know, this is all on that sheet. I'm not, you have to memorize any of this. Anybody got any questions about the 2900 to 3100 region? The 2000 to 2300 region, this is where we're going to find CC triple bond and C triple bond N. There's nothing else in this region. So if you've got a peak here or you don't have a peak here, then you know exactly if you've got that C triple bond C or C triple bond N or nothing there. All right, so it's either going to be there or it ain't. Anybody got any questions? Another really useful one is 1700 to 1850. That's where we find C double bond O. Again, nothing else absorbs in that region, just C double bond O's. That one is really useful. Those are usually strong, usually sharp. Sometimes they're a little bit wide, but not too wide. Generally C double bond O. I mean, usually sharp. And then we can move into distinguishing different kinds of CC double bonds. Now, if we know that we can know we've got C double bond Cs if we've got this peak here. If we've got a peak between 3000 and 3100, then that's going to indicate that we have a C double bond C. But you know, this is for the CH stretch. What about the C double bond C stretch? Well, that's going to be between 1500 and 1650. I mean, we're looking at two different kettles of fish here. We get two different kinds of peaks, one for the CH and one for the C double bond C. Now, the way to distinguish them, if you've got a C double bond C that's part of a chain, that's going to be at approximately 1650. But if you've got a C double bond C that's part of an aromatic ring, you'll find those kinds of peaks between 1500 and 1600. So that will help. That's helpful. If you know you've got a C double bond C and you want to know what kind of C double bond C it is, that's how you can figure it out. Does anybody have any questions? Now, you can only do this if you know you've got a C double bond C in the first place. All right, so this doesn't count because other things do absorb in this region, in the 1500 to 1650 region. There's a lot of other stuff that can possibly be there. So you can't just look there and say, oh yeah, that's a C double bond C. What you want to do is figure out, first of all, if you've got a C double bond C by looking in the 3000 to 3100 region, and then see what kind of C double bond C you're dealing with. Does anybody have any questions?
Yeah, I do.
Yeah.
So I'm looking at I just kind of grabbed the tables that I printed out that you said we're going to have.
Mm-hmm.
And so on some of these tables, like the yellow ones I'm talking about that are here.
Mm-hmm.
So I'm looking at the C double bond Cs, which you're telling me are in the 1500s.
Yes.
And underneath the C double bond C on one of these, it says 7567. And underneath the C double bond C on another one of these, it says 150 ppm. So I don't understand what I'm reading.
Well, there's only one that refers to this is the only one that refers to infrared.
Okay, so the ones that I have here are NMR, is that what you're saying?
Yes, that's correct.
Okay, so the infrared is only this one.
Yes.
So they are actually different in the way you read them.
Oh, yes.
Okay, I didn't realize that. That's
very different.
okay. I thought that the scale at the bottom was the same.
Oh, it ain't.
Okay, that's good to know. So we have them both, but the scale is not the same.
Yeah, that's right.
Okay.
So I've actually got all that on this on the correlation chart. You can see that C double bond C stretch aromatic, C double bond C stretch chain. And you can see where those are expected to be. All right, any questions? All right, but what you really want to know, what you really want to know is how I'm going to ask questions about it on the test, hey? All right, let's get this out of the way here. Here we go. So on the test, you're going to have problems that look a lot like this. This is actually in problems test 4, page 50. So this is an exercise. There's 9 problems here. They have answers as well. All right, so number 1, it says C5H12O, draw 6 compounds that fit with that data. Okay. Now, before I get to solving this, there's one other thing I want to go through, which I don't think I have yet. And that is units of unsaturation. So units of unsaturation, what this will do is it allows us to take a molecular formula and be able to figure out how many double bonds or rings might be present. So let's go through that first, because that can be incredibly powerful in giving us some information. So if you had something like this, this is C4H10. It doesn't have any rings or double bonds on it. I mean, I could put the hydrogens on just for kicks. But I would call this saturated. And by saturated, I mean it has as many hydrogens as it can possibly take. So that's what saturated means. Doesn't mean that it's all wet. It just means it's got as many hydrogens as it can have. You might have heard of polyunsaturated vegetable oils, right? Well, that just means vegetable oils that have lots of double bonds in them. They don't have as many hydrogens as they possibly could have. Okay. Now, if I was to turn one of those single bonds into a double bond, what you'd notice is that it would cost me 2 hydrogens to do so. So I'd say that's not saturated anymore. That'd be C4H8. So 2 hydrogens it costs to do that. Now, if you were to make that into a ring by tying up one end to the other, that would also cost 2 hydrogens as well. And you can see that would have the same formula, C4H8. So what's the bottom line here? So for every, if you know what it is when it's saturated, for every double bond or ring you have, you lose 2 hydrogens. So that's it. I mean, that's what units of unsaturation is about. Now, there's certain rules that apply here as well. And for each halogen, halogens take up as many spaces as hydrogens do. So if you had something like this, you can see that the Br would take up as many spaces as a hydrogen. So for each halogen, you add 1H. Nitrogen has 3 bonds, and for that you subtract a hydrogen for each nitrogen. And oxygen doesn't have any effect on the calculation, because oxygen can just be shoved in anywhere. So let's have a look at how we might apply that. Well, the other thing is, if you've got 4 or more double bond equivalents, you can automatically assume that you've got an aromatic ring. So that's got 4 double bond equivalents. And I know you see if 1, 2, 3 double bonds in the ring makes 4. So that's good information as well. All right, so let's have a look. We use this formula here: saturated hydrogens minus effective hydrogens divided by 2. So let me show you some examples here. So what we do is we say C4H8O2. We know that oxygen doesn't have any effect, so it just becomes C4H8. And then we need to figure out what it would be if it was saturated, so it'd be C4H10. And the way we do that is saturated always has a predictable formula. It's CnH2n plus 2. So if you have, for example, here 4 carbons, then 2 times 4 plus 2 is 10. So that's what it would be if it was saturated. So then what we do is we subtract those two, 10 minus 8 divided by 2, which equals 1. So we know that C4H8O2 would have 1 double bond equivalent. Now, I couldn't tell you if it's a ring or a double bond, but I can tell you it's just got one of those. Does anybody have any questions?
Why did you divide it by 2?
Because it's kind of like up here, each ring or double bond costs 2 hydrogens.
Oh, okay.
Let's see, C6H4Cl2. That would be C6H6 because each Cl would be just take up the same number of spaces as a hydrogen would. If it was saturated, it'd be C6H14. The 14 is 6 times 2 plus 2 from up here. (14 minus 6 divided by 2 equals 4. So that'd have 4 double bond equivalents. So that would most likely be aromatic, as I showed you earlier. Anybody have any questions? And the last one here has nitrogen in it, C5H5N. Now the rule is for each nitrogen, you take away a hydrogen, so it becomes C5H4. If it was saturated, it'd be C5H12. So that would mean that it was going to be 12 minus 4 divided by 2, which is 4 again. Does anybody have any questions? Okay, I've got a video on that. If you're confused by it, you should probably watch the video again.
And that's on the sheet too, right?
It is. Actually, Julie, yeah. Along with an example. So really, again, nothing to memorize there either. It's a gift. All right, let's go back to what I was doing. Sorry. I hate how bloody Zoom thinks it's smarter than I am. All right. Let's look at this example. You can see why I went through units of unsaturation. We've got C5H12O. That would be the first thing I would do, is figure out what the units of unsaturation were. So oxygen doesn't have an effect, so it just becomes C5H12. If it was saturated, lo and behold, it'd be C5H12. So it'd be 12 minus 12 divided by 2, which is of course 0. So what we know is that C5H12O doesn't have any double bond equivalents. So there's no rings, no double bonds. I think that's fantastic information. Does anybody have any questions? Any questions? Okay. So what we would need to do first is look at the infrared spectrum here and see if we can figure anything out that might be useful to us. So here's what I like to do. I like to kind of do a checklist because this pretty much covers everything anyway. So I like to do OH, NH, and NH2. I like to see if we have CH stretches connected to CC double bond, CH connected to CC single bond. Those are important. C double bond O. Yeah, I think that's pretty much it. So I like that. All right. I know I didn't include some of the stuff on there, but for pretty much all you'll see, this is what you'll need. All right. Can anybody tell me why? Can anybody see that there might be something here that could be eliminated immediately? Any thoughts?
Yeah, the double bonds.
Well, let's yeah, yes, Julie, but let's look at something a bit more obvious. Any thoughts? Things that could be eliminated immediately.
Well, there's nothing in the 2000 region.
Oh no, again, something simpler than that, Rebecca.
Okay.
Look at this list here and tell me what could be immediately eliminated.
Well, there's no ends in it.
Oh, there's no ends. Oh, how do you know that, Julie?
It's at the formula, there's no ends.
Oh, there's no formula. There's no N in the formula? Yeah, okay, so now you can see what I mean. There was something really obvious there that you can look at in order to get rid of those. All right, so what we do, let's look at the correlation chart here. And you'll notice we have this whopping peak here at about, looks like about 3,400. And that would lead me to believe that I had an OH stretch. So I think I have an OH in my compound. Then I look at the 3000 region, and you can see that it doesn't straddle 3000, which tells me that it has alkane, but not alkene. Take a look at the one below. Do you see how that peak kind of straddles 3000? That would mean that both of those were present. But since this one doesn't straddle 3000, we've only got alkane, but not alkene. Does anybody have any questions? Okay, just for kicks, I'll add a couple more little notes here. Now, this is not something you have to memorize. It's all on the correlation chart. Okay. Do you think we have C double bond O present? Do you see anything between 1700 and 1850?
No.
No. So there's no C double bond O. Can anybody tell me why you wouldn't expect to see a C double bond O? Why you weren't going to see one anyway?
Because of the calculation we did?
Yeah, because it said no double bond equivalence. So there can't be any double bonds at all. So I found exactly what I was expecting to find right there. No C double bond O's. I'll tell you what, I'd be certainly concerned if I had figured out there were no double bonds, but then I saw a C double bond O, I'd begin to wonder something then. Might have screwed up something along the way. All right. I'm going to, well, it's kind of hard. All right, I'm going to go ahead and just do it. So I have to come up with something that obeys all the data I have here. No double bond equivalence, C5H12O, has to have an OH, no rings, no double bonds. So immediately, this can be what I might draw. I'm looking for 6 possible compounds that would fit this. That's one of them. So you might say, okay, well, let's go ahead and just move the OH along the chain. Nothing wrong with that. Now I can't move it here because that would be the same. So I've come up with 3 so far. I need to come up with 6. Oh gosh. Ooh. Can anybody guess what I might have to do now? Any thoughts? All right, so what I can do is I can branch. I can do this kind of stuff. What about this? Is that okay? How about this one here? Can I draw that? C5H12O. Is that
No,
okay?
it doesn't have an O.
It has an O. I see an O, Rebecca.
Oh my gosh. Okay, sorry. I thought that's where your marker got stuck.
No, it's got an O. So, no, it's got an O. Can I draw that one? Is that a possibility or not?
I'm thinking maybe yes, if the H is attached to the O and you just didn't.
Well, how many bonds do you see attached to that O in the
Oh,
structure,
two.
Julie?
Yeah, you couldn't do it.
No, I couldn't have an H on there. And it's customary. If there's an H on the O, I always draw it in anyway, right?
Yeah.
Yeah. So is this legal or not?
No.
No. He's illegal. Because he doesn't have an OH. He had to have an OH. So you can get an idea. You can draw anything you like as long as it obeys the parameters that you calculated, like the double bond equivalence, and then what's in the IR. You know, does it have an OH?
Yeah, but there's no way to get another one, is there?
Oh yeah. Yeah. I'll show you one other here. So that's different. So you can see I can put the OH pretty much anywhere there, Julie. Anywhere on that structure. And it comes out to be different. There's lots of different things I could draw, probably about 10, actually. I'm only after 6.
And did you say the second and third one that you drew were the same?
No, I said if I put the OH here,
Okay,
right, that would be the same as this.
all
That's
right,
what I
that
said.
makes sense. I looked down while I was drawing and I
Oh,
thought I
okay.
heard you say they were the same. Thank you.
Oh, no, it's all right. Any
Okay.
questions? Any other questions? So I've got 9 examples here, and I'd recommend you kind of look at all of them. They're all right. Okay, let's take a look at a test question just for kicks. Here's one. So this one is C10H14O. Yeah, I'm not really expecting you to be able to do this whole double bond equivalent thing quite yet, but it just takes practice. So C10H14O, that would be the same as C10H14 because oxygen doesn't have any effect on the calculation. And if it was saturated, can anybody tell me how many hydrogens it would have if it was saturated? Remember, it's CnH2n plus 2.
22?
22, right? 2 times 10 plus 2 is 22. Any questions? All right, 22 minus 14 divided by 2 equals 4. So there's four double bond equivalents, which would immediately tell me that I have an aromatic ring. So using that checklist I was just showing you, so you got OH, NH, NH2, alkene CH, alkane CH, C double bond O. Now there's no OH, and we know there's no NH or NH2 because, well, there's no N up here. We have alkane and alkene CH present because you can see it straddles 3000. And there's no C double bond O because there's nothing in the 1700 to 1850 region. So I'd have to come up with some structures. So why don't you see if you can come up with a structure that has this molecular formula and obeys the information we have here, remembering that if it does have alkene and alkane CH, we definitely do expect to be able to use this aromatic ring. So that's my clue to you, is that it has an aromatic ring.
Can I ask a question?
Yes, Julie.
Well, since it has the aromatic ring, so the C double bond CH, the alkene CH, that is the ring, right?
Yeah, well, it's part of it.
Yeah, okay, but it has to be because there's only 4 double bond equivalents, right?
Right.
So it can't have any extras. It's got to be the ones that are in the ring.
Oh, yes, that's true too. So yeah, you can't just throw anything else on. You've already used them all up, yes. Is that what you're saying?
Yes.
Yes. So see if you can come up with just one. I'm just looking for one structure that fits. Just one. One measly structure.
Did you rule out the OH because there wasn't a deep
Yes, that's exactly
stretch
right,
at
Rebecca.
3000?
Yes, that's right. There ain't nothing there. So there ain't no OH.
But we do have an O in the compound.
We do.
Okay. All right, thank you.
I think it just twigged exactly what you have to do now. I'll give you 30 seconds or so to come up with something. Looking for just one compound here that would fit. All right, how many carbons does the aromatic ring take care of? Any thoughts?
6.
6. So how many do we need to take care of?
4.
4. So I'll just put 4 on the end here. But I also need an O, but it can't be an OH. So I might do something like this. 1, 2, here we go, 3, 4. So that would fit. Now I could put the O here, I could put the O here, I could put the O here. That would be possible as well. So those would all be possibilities. There's another possibility too. We actually don't have to have just one thing on the ring. We could have something like this. And that would fit. And this would be different as well. You can see that then the possibilities become quite great once you realize you can move stuff on the ring and you don't have to attach just one thing or 2 things even. You can attach 3 or 4 and still come out with the same formula. So I think I asked for 4 compounds. There's probably about 16 you could draw that would fit.
Don't you have to take the H's into account when you're doing
They're all taken care of. I mean, if you take a look at this, Julie, 1, 2, 3, 4, 7, 9, 11, 14.
Okay.
So as long as you've got the double bond equivalents correct, the hydrogens take care of themselves. I'll say it again, Julie. As long as your DBE is right, the hydrogens will take care of themselves. Every time. Every last one of those structures has C10H14.
I have a question.
Yeah, Deanna.
You said if the number is 3 or more, then it's automatically an aromatic ring?
No, if it's 4 or more.
4 or more? Okay.
Yeah, and the ring, you can see it, and it's got 3 double bonds and the ring makes 4. So it covers 4 double bond equivalents.
Can you say that last part again? Because I wasn't really understanding the 4 double bond equivalents.
Okay, 1, 2, 3 double bonds, and the ring makes 4. Well, this would have 3 double bond equivalents, right? That's
Right.
3. That's 3. But if it's inside the ring makes up for 1 double bond equivalent. Double bond equivalents don't have to be rings. They can be double bonds or rings.
I think maybe I'm reading it too literally. I'm looking for a 4th double bond.
Well,
you're
that's the
saying-
thing, that a ring counts as well. A ring counts as a double bond equivalent. That's why it's called an equivalent, not a double bond itself.
Okay, it's not number of double bonds. It's things that,
Rings or double bonds.
okay, I remember that. Thank you.
Any other questions? Any other questions?
So if it were a 3 double bond equivalent, could it still be a ring or no? No. You'd have 3 double bonds, but having the ring would have to count as the 4th equivalent. Is that
Yes,
correct?
that's what I'm saying.
Okay, thank you.
If it had 3, I couldn't tell you. It might have 2 double bonds and a ring, 1 double bond and 2 rings, or 3 rings. I don't know. I couldn't tell you. But what I can tell you, if it's 4, you can always go for the aromatic ring.
Okay, I understand what you're saying. It could still have a ring, that would be one of them, and then maybe 2 other double bonds in the structure, or 1, and okay, I get it. Thank you.
It's all a bit of a mystery after that. I don't know. But you know, having the 4 really makes a big difference, because then you can just generally just say, oh yeah, here we go, aromatic ring, and you've accounted for everything. All right. Any other questions? Any other questions? Okay. Well, I've given you the basics there. I know a lot of you have already done infrared in the lab as well, so you had a bit of exposure to it there. Probably not in this form, but you know, now you've got at least some grounding. I have videos about this too, and videos that have these problems too, so you should look at them as well. How people do on this, it's usually mixed. About, I don't know, half the class to 2/3 does okay. The other people tend not to do as well. It all depends on how well you understand it. If you understand it well, it's fine. If not, you're going to struggle. It's really that simple. Does anybody have any questions about infrared here? Okay. Okay. So Rebecca, you were asking about the NMR videos. They're all here too, from how NMR spectra are obtained all the way down to the end here. These are all NMR videos.
Okay, so watching those before the lab on Wednesday and the lecture would give us our best shot. Okay.
I think
Those,
so.
is that the mini lectures that you're in?
Yes.
Yes, okay.
And it's the same, I've got links to the same videos in the lab.
Okay.
All right. There's nothing different about them. They're the same ones.
Yeah. I just remember when we were doing it last week, you had said at least make sure to watch the first 2 videos, and I didn't know if it was that way for this one, but that's fine. Okay.
I would say, I'd say 4. I'd say watch these 4.
Okay.
All right. And I'm just going to show you a little bit here about how NMR spectra are obtained. Now, NMR stands for nuclear magnetic resonance. I think you've all heard of MRI, magnetic resonance imaging. You know, it's exactly the same technique. But you'll notice that this is nuclear magnetic resonance. So the word nuclear for you would freak people out because they think it was something to do with radiation, which it is, but not that kind of radiation. But they knew people would freak out, so that's why they changed the name of it to MRI, magnetic resonance imaging. It's the same thing. There's nothing different about it at all. All right, I know you've all heard of MRI. All right, so let's take a look at how NMR spectra are obtained. MRIs use the same kind of magnets and everything else. So. All right, now I'm not going to play the whole thing. I'm just going to give you some highlights of it. Oh, hang on. Let me just fix something here.
Technique for finding the structures of organic compounds. So much so that there is a saying, when the NMR goes down, the organic chemists go home.
Yeah, I wish. That's true though. I mean, NMR is very useful if you don't, it's a great way to be able to, if you've made a compound, to be able to figure out what the compound is, you go ahead and you stick it in the NMR machine, come out with the spectrum, and then you can come out with what the structure is.
The principle of NMR is based on the fact that certain nuclei with odd atomic mass or atomic number, such as hydrogen-1, carbon-13, fluorine-19 and phosphorus-31, have a property called spin. This means that they have a magnetic field similar to that of a bar magnet. When placed in an external magnetic field, these nuclear magnets can line up in one of two ways, with or against the applied field. These two different states have slightly different energy levels. Electromagnetic radiation, which has an energy corresponding to the gap between these two states, can cause these nuclear magnets to flip from a low energy state to a high energy one. The size of the energy gap determines the frequency of radiation required. Each element has its own particular frequency.
So I know that sounds really complicated. So let me simplify it just a tad, okay? They don't do the best explanation of this. It's all right. I mean, it's not like it's inaccurate or anything. It's just a little bit hard to understand. So what it's saying is each of these hydrogens is like a little bar magnet. That's all. It's a little bar magnet like this. So if you've got hydrogens in a solution, they're little bar magnets that look like little arrows like this. And they can be anywhere and go any which direction they want. And then if you apply a it has to be a really strong magnetic field, what I'm calling B. What happens is they will line up with and against that field like that. There's no way to predict which way they're lining up. How many have we got there? 6. But you know, about half of them will line up one way, half of them line up against the other. And then what we can do is we can irradiate this with radio frequencies. These are radio waves here. And what the radio waves will do is they'll flip the arrows from up to down and down to up. And the frequency of these radio waves will correspond to the energy required to make that flip. But further, if that's correspondent to the kind of hydrogen it is, what kind of environment it's in. what kind of functional group it might be attached to, all sorts of other things. So it actually adds a bit of predictability to it.
But they all lie within the radio part of the spectrum. Yet slightly different.
So
This
this
energy is picked up by a
this is ethanol, for example. This has got 1, 2, 3 different kinds of hydrogen here. I know that there are 3 hydrogens here, but they're all in the same environment. These are in the same environment as each other, and this one's in a different environment. So these all will have different frequencies. So let's see this part here.
This energy is picked up by a receiver in the instrument and looks like this. A strong signal gradually dying away. This is the total signal from all of the hydrogen nuclei in the sample and is very difficult to interpret. However, a mathematical technique called a Fourier Transformation can be used to separate out the signals from hydrogen atoms that are in different molecular environments and present them as a spectrum that can be interpreted by chemists.
So that's what an NMR spectrum looks like, just a bunch of peaks here. And then you can use that information to be able to determine what the structure is. That's the very basics of it. The NMR machine itself, very expensive. They run about $500,000. Maybe not quite that expensive these days, maybe a little bit cheaper. Still, they use a very strong superconducting magnet, which requires really low temperatures to work, and it requires the use of liquid nitrogen, liquid helium, and these have to be refilled every so often. We don't have an NMR machine at St. Pete College. We never will have one. It's just too expensive and it costs too much to maintain. So the main focus here is for me is just being able to show you spectra and then show you how to go ahead and interpret them. All right, so that's all I want to cover today. I will talk on Wednesday about how to interpret NMR spectra. This just gives you some very basics about how we take them. All right, so anybody have any questions?
Yeah, I do.
Yeah.
Would you use either IR or NMR?
Probably both.
Why would you use both?
Well, IR would tell you what kind of functional groups you might have. NMR would allow you to confirm that. One can never have too much information, Julie.
Okay.
All right. Any other questions? All right, that'll do for today. I will see you all on Wednesday, and if you're in my lab, I definitely hope to see you on Wednesday. I'm going to send out an email to that effect to my lab people. All right.
Thank you.
I'll see you all later.
Thank you.
Thank you.
Have a nice day.
You too.